Okay, let us start. And so this lecture will be, I think, an easy lecture. We will just, there are a bunch of problems here. We will prove that they're all NP complete. And we already did a few last lecture. So we will believe that 3 set is NP complete. It's the task for next lecture to prove, or actually maybe even 2 lectures to finish this proof. But now we believe this, and we make and recall that last time we sent. So the definition of NP complete is that we can reduce every problem from the class NP to this problem. So this problem is harder than any other problem in the class NP. And so we can have here that what's intuitive picture. We have NP, and the problem is NP hard. For example, the health problem. So this was a task in previous seminar, if I remember correctly. Prove that the halting problem is NP hard. And so for this, you have to build a reduction from any problem in NP to the halting problem. So, but how can we prove that certain problem? So what is an NP complete problem? Problem that is inside the class NP, and that's also NP hard. And so to prove that the problem is NP hard, so every problem in NP goes, we make, so here is some, let's say 3 set. So we will make an explicit reduction from every problem in 3 set. However, if we have a new problem, like the independent set problem, we can build a single reduction from 3 set to independent set problem. And then by transitivity of reductions, so we can compose reductions, which we presented last time, we have a reduction from every problem to the independent set problem. So what is a reduction? That was polynomial time computable function with 2 properties. Well, I already said one. It's you can compute the polynomial time, and second one is that it transforms problem instances of one problem to instances of another problem with the same answer to the question. Oh, this is equivalent. And so this is what we will be doing today. So we will believe 3 set is NP complete, and we will go over this chain of reduction. Last lecture, we went from 3 set to independent set, and independent set to clique, from independent set to vertex cover, and from vertex cover to dominating set. By the way, I made a mistake in the reduction last time. So I said that, so remember the dominating set problem. So you're given a graph and a number k, and the question is, find k nodes so that every node not selected has a neighbor among these k nodes. It was dominating set problem. And so input is a graph and a number k. And then the question is, can you find, for example, 2 nodes so that every node that's not among these 2 nodes has a neighbor among these 2 nodes? And here it is the case. And then I said, let's make a reduction from vertex covered problem to a dominating set problem. And I said, let's, for this reduction, I said, let's insert in every edge, let's insert 2 nodes. And this was almost correct, but my proof had a mistake. And nobody spoke about it, so you need to pay more attention. But it was the very end of the lecture. Okay, and the number here was k plus number of edges. So this was the reduction from vertex covered to dominating set problem. And so where was the problem? I said that, okay, so problem is that if a dominating set exists of a given size, then we have a vertex cover So in the backward equivalence. So know that when we prove equivalence, again, we have to prove two directions. If we have vertex cover, then we have dominating set. And if we have dominating set, there is a vertex cover. And then I said, okay, for any dominating set, we must have one node among the two nodes in each edge. So every edge must have a node here. And after we drop this node, we see that the remaining set is a vertex cover. But this assumption was wrong, because it can happen that the dominating set might contain this and this node. And on this edge, none of the two internal nodes is selected. But it's easy to fix because we just have to make a triangle on each edge. And now the claim is true. So now this node doesn't have a neighbor among the selected ones. You are forced to select two internal nodes. And so both directions now work. So in this other direction, we had to say, okay, if there is a vertex cover, then we select a node on each edge. We select a node that is away from the node that's covered by the vertex cover. So, for example, okay, let's do the same example. So here we have a vertex cover here and here. So of course, this is not a part of the input. The input doesn't have the vertex cover and dominating set. Okay, but so in this example, is this vertex? Sorry, this is not the vertex cover. So now we have vertex cover. So these three nodes are already selected. And how do we choose the nodes on the edges? Each time we choose the node away from the node that's covered of the edge. So vertex cover, every edge already touches one selected node. So that means in each node we can select this node, this node, this node, this one, and this one. And now we are good. And so we selected one and we have dominating set in this example. Okay, so this was fixed for last lecture. So now our goal is to go through this chain of reduction, explain the chain for Hamiltonian, not path, but Hamiltonian cycle problem. And I will use that directed Hamiltonian cycle. And so undirected, I will quickly say how it works. And this I will remove with that last to have a bit more space.
Directed.
Huh?
Directed Hamiltonian cycle is also directed Hamiltonian cycle. Just we add two edges to the one. Like each edge becomes two edges. Well,
yeah, but our reduction will not have the edges in both directions. So we will reduce to a harder problem. And then the undirected graph is an easier problem. So we have a little bit work left. It's not so difficult. I will quickly say how to do it, but there is some work. Yeah. Okay. So first, let's recall what is the three-set problem. So we consider Boolean formulas. They're built from and or not. And a clause, remember what is, okay. So literals are either the variables or negated, the negation of variable. So then clause is an or of literals. And a formula in 3CNF consists of clauses with at most three literals. A conjunction, so an and of clauses of three literals. And so let's do an example. X 34, not Y or Z, and not X or not Y or Z. That's a bit stupid. And X or Y. Okay, so this formula, it has three clauses. And all the clauses have length 3. Okay, let's do one more so that you're not confused. X or Y. Or Z. Something like this. Okay, so now there are 4 clauses, each of length. Let's do a bit shorter clause, which is also allowed. Okay, so this is 3 sat. So formula in 3 CNF. So the 3 sat problem is so the input is formula I in 3 CNF. And then the question, is the formula satisfiable? It is can be assigned zeros and ones to the variable so that it evaluates to 1. Is 5 satisfiable? Okay. Now the next problem is called not all equal 3 sat. And what is asked here, an assignment in which every clause has both a true, at least one true and at least one false literal. Every clause has at least one true and one false literal. And so what's forbidden, all zeros and all ones. Before, only all zeros were forbidden. And so in the normal problem, if a clause has 3 times 1, it's okay. Now not anymore. Okay. So so the input is the same. And the question, assignment. Okay, I will write it later. Let us ask a question. So we will do the reduction into 2 steps. We will first start with not all equal 4 sat. So the input is a formula in 4 CNF. Clauses can have 4 literals. And here is an easy reduction. Not all equal 4 sat. So 3 sat reduces to not all equal 4 sat. There should not be a dash here. So it's mostly written. Okay, so how do you reduce from 3 sat to not all equal 4 sat?
You just add clauses.
Add
If
the
all
variable.
variables are all variables are equal, so we should expand that equalities into.
Okay, so there are some good words, but no consistent explanation. Somebody else? Maybe at home? It's good to switch your camera on because then you have less chance to fall asleep. And also, if you fall asleep, I know something is wrong. I mean, not if one falls asleep, but
If all variables are equal, we can make another one. Inverse them.
okay. So my input is a formula here. My input here is also a formula.
Okay, equality can be written as for variable for literal clause.
Yeah, so I need to change the formula to go to not all equal 4 sat. Maybe we're lucky, we can just leave the same formula, but then it's strange. Why do I insist on 4 sat? So you should add something to the clauses. Yeah,
One variable.
exactly. Yeah. Every clause, we will create a new variable and add it to every clause, and this is enough.
We add, well, if we have a clause, we take one variable and add its negation into the clause.
It doesn't matter whether we add it negated or not.
Yeah.
So we have
Yeah,
and
No, that's true.
or a.
Uh,
Okay,
So what is the purpose of adding additional variable?
yeah. So
Purpose
yeah. So he said why it works.
works because why it works? I
Yeah.
don't know.
Okay. Somebody else?
well,
Why
wait,
does it work?
Uh,
I mean,
We are simplifying tasks or what?
Yeah, so we said what is the reduction? We start from the formula and we add the things in blue. And so this is our input for this problem. And now, okay, clearly in polynomial time and second property, answers are the same. So why are the answers the same? So two directions. Let us start. Imagine that this has satisfying assignment. Then there is an assignment in which every clause contains opposite literals. Why is it true? It's very easy command. Wake up. Wake up. So in the black formula, we have an assignment that has at least one in each clause. Okay, how will we choose A? So that in every clause we have both 1, at least 1, and at least 1, 0. Of course.
Are equal with numbers.
Yeah. So yeah, that's the second part. You got it good. So A we set to 0, and then we have a not all equal assignment because every clause has a 0. Exactly. Okay, so if this has assignment, then here we also have yes. Now the opposite direction, and there we use your argument. If we have a not all equal assignment, then note that if we flip all the variables, it's still not all equal assignment. So if we have 0, if this not all equal assignment A is equal to 0, then the other variables are a satisfying assignment because the A doesn't help to get 1 anywhere. But if A is 1, we flip everything and then we apply the same argument. So good. Then, okay. And now we need to go from not all equal 4 set to not all equal 3 set. This is a little bit harder, but not crazy hard. So I will explain what will happen. So let us take any clause. So A union X union Y union Z. Okay, I take all positive ones. You will clearly see how to add negations. So the idea is that we replace one clause by two clauses by adding an extra variable. Let's call it U. And the added variable I will call A. So we will use A UX and not A, Y, and Z. Like this. So one clause of length 4 becomes two clauses. And each time we break a clause in this way, we create a new variable. Okay, so claim is that in an assignment where we have both a 0 and a 1, right, to write it beautifully, then we know how to choose the value of A. And so imagine that we have an assignment where we both have a 0 and a 1. Say U is 0 and Y is 1. How will we choose A? Well, there are two cases. Either U and X are equal. Then we choose A, the opposite value. And then this has different assignments, but also this one has different assignments. So we assume that these are equal. Then these are different. But this means that these are different. And this means that one of them is also different. So here we have not equal. Not equal. Here we have, of course, not equal. So that means that so we have 3 times not equal. So they're different. And so when we go from imagine that Z is different, Well, it's already clear because one person is falling asleep. And so if we have an assignment where we have different elements here, then we choose A. So if U and X are different, then we are good because we are already covered for this clause and we can freely choose not A here. But if U and X are equal, then also no problem. Because then one of these are different. And so we can choose A opposite from what we have here. Okay, so this reduction is done. And so we have reduction from 3 sat to not all equal 3 sat. And so now let's go to tree colorability problem. So it was the problem in the beginning where at the first lecture. And so I said if you're given a graph and polynomial time, you can know if you can color it in 2 colors, yes or no. But to prove that you need 3, whether you can color with 3 colors, it's no sub-exponential time algorithm is known. Okay, so let's prove this one. So input is now not all equal 3 sat instance. And the question here is input the graph. Okay, I don't need to write it. Okay, and so for this, we will use a construction with gadgets. So given a formula, a 3CNF formula, we need to, let's keep the formula above. So here is a little formula. We need to build a graph. That's it. So graph will consist out of variable gadgets and clause gadgets. So for every variable that we have, we will make an edge and label one node by X and not X. Should I write bigger for home? Probably. Yeah, that's a good one. X and not X. Y and not Y. Z and not Z. So that's a variable gadget, and all nodes will be connected to the same node so that I force one of 2 colors. Let's say that we use red, green, and blue. It doesn't matter. And now the closed gadgets will be triangles, and all the nodes are labeled by the clauses. Like this. X, Y, not Z, and then, oh, this is not a triangle, but we can
add a fake.
yeah. So we can repeat some literals. Then nothing changes.
Then
In the not all equal 3 assignment, and then we have again a triangle, just with the repeated literal. It's okay. And not X. Okay, and now we connect nodes to opposite literals between the gadgets. So Z will be connected to not Z. And let's use a different color. So Z is connected to not Z. And X is connected to here, Y is connected to here, and so on. Okay, I will not do it, and so on. You get it. Okay, that's it. That's the reduction. So clear. So there are variable gadgets with a special node, and then closed gadgets, and the literals are connected. Okay, and so now the claim is that this reduction is equivalent. So if clearly you can do it in polynomial time, because number of nodes is and not at most twice number of literals at the number of variables times 2 plus, I mean, you got it here. Okay, why it's equivalent? So let us assume that we have not all equal assignment here. Then we will set all true literals in the variable gadget to say red, to green, and all the false ones to red. Okay, and here we will have a true and a false literal in every clause. The true one goes to green, the red one goes to false, and the remaining one goes to blue. And this one also goes to blue, the special one. And then we have tree coloring. Okay, this is just by construction. And so every edge is okay because all the edges from this one only connect to red or blue, green or red, and this one is blue. All the edges, the black edges connecting clause and variable gadgets, they connect opposite literals. So they are green and blue on the other side, or they connect the blue node here. And in every triangle, we have 3 different colors. Okay, and now the opposite direction. And so if we have assignment, we have coloring. If we have coloring, then we have assignment. And so we can permute the colors and say that this one is blue. And then we will say that all the green in the rest of the picture is true, all the red is false. And then since we have triangles here, we must have red and blue here, and we do have an assignment. It can never have it. So how do we read out the assignment? For this, we need to know that all appearances of Y are consistent with appearances of not Y. And this is guaranteed by the variable gadget, because every literal is connected to opposite literal and variable gadget. So, okay. And so we will never have not white to green and white red. It will never happen because they are connected by opposite literals, and then we have a cycle of length, a triangle actually. Okay. So that's done. Oh, we have done this, this. And now the next problem is called positive 1 in 3 set. Here, the task is that in every clause there should be exactly one variable that's true. And moreover, we cannot use negations. So if we remove positive here, then problem is even harder. So still NP complete. So here is positive 1 in 3 set.
Each literal is positive.
Yeah, only positive literals. Assignment.
Can we select exactly one variable from each clause?
Yeah. So one variable should be true and the other should be false. Right. And here for our reduction, we don't need 2 is okay. Okay. So now we reduce tree colorability to this problem. So the input is a graph that's tree colorable, and we have to write down the formula. Okay, and I think you can write down the formula yourself. It's so logical how to do it. And so you need a formula that is satisfies this assignment if and only if it's tree colorable. So being tree colorable means that there exists an assignment of colors and you have to code all the constraints on the colors. And so edges have to connect nodes of different color, and every node should have exactly one color. So you need to choose variables and then build a formula. So what is your reflex? What variables will you use?
Variables are nodes.
A little bit more. So you need to,
Color of every.
Yeah.
Every
For
color,
every color and every node, there is a variable. And the variable is 1 if this color is chosen. Yeah, exactly. So, okay, I didn't write the question. Okay. So, now we need the graph. Let's use the usual graph. Oh, A, B, C, D, E. And then we have variables X, V, C. So V is no. Or actually, no V. And then for all C and RG. Okay, and then what are the first? So we have two types of clauses. First type of clause will guarantee that at least exactly one color is selected. So we will use XAR, XARG, XA. And this is continued for all the nodes of the graph. Same for B. And then the second batch of clauses guarantee that edges connect nodes of different color. And so how will we code them? So these constraints. Oh, it's a little tricky, yeah. So what is the first idea that doesn't work?
Two clauses with two clauses, two variable clauses with just work. Like if we add, say, XDR or XD.
Oh, so let's look to this
XDR, XD, like B or XE.
Oh, sorry, yeah, there's something
B.
else. Yeah, okay, that's you have it fixed, yeah.
No,
No?
the B, and then
Yeah, sorry, yeah,
and
DB.
XE. The third color.
Yeah. And then XE. Oh. No, your first, I think this works. Let's check. So we look to the HE.
No, if one of the,
XEG, no?
no, if we have one of the, no, it should be just green. Not works.
XEG.
If G is. Yeah, and we add such clause for each like permutation of.
Oh, wait, let's drop the positive here. So then it's easy, right?
Yes.
Yeah, then it's easy because we can use XV and here X X.
And X. Well, it's then we could just
Yeah.
two.
Yeah, but just I forgot a little bit how it goes, so I made the problem if XR, yeah. And then we do the same for the blue and green. And so if they're both red, then we have two zeros. But actually doesn't work because if they're green and blue, then so if this is green and this is
But
blue,
we add such clause for each color.
yeah, so it's not working, yeah.
Why?
Yeah, because we can have 2 times 1 here. If this is green and this is blue,
Okay.
no, this is 2 times 1 and it has to be exactly 1 in 3 set, even if we draw positive. So this idea doesn't help us, so I will place it back.
So what doesn't work about what I said before? Like if we had two colors for one node and one and like the third color for which else?
The other node, so R, G, X, and T.
Well, yeah, it doesn't work because it
Yeah.
can have two positive values. Okay, then you're right, and it should be not B but R or say G.
Yeah, but that's also not working. So we need to do something else.
Wait, if we write R there.
Here
why
are,
does- Yeah, R. Why doesn't it work?
so look,
If we have
we have too many possibilities. So we can have, so they can be all 3 to 0.
yeah.
Yeah. So yeah, you know?
No.
Okay. No, the solution is let's create a dummy variable that can have both values. So if they're both to 0, then the dummy variable just add a new variable here. Okay. How will I call it? Z1.
And we add such a variable for each.
Yeah.
Ah,
So now we cannot set both these nodes to red, and then we do the same for green and blue and for all the other nodes. So, okay. Yeah, so we are done with reduction here. Okay, so it's good, that keeps you awake. I mean, that's the life you think for a long time and understand solution is easy. Okay, now reduction from positive 1 and 3 set to subset sum. Okay, what is subset sum problem? Oh, but by the way, let's give away the seminars. Or if you find the lecture boring, you can solve the problems. Yeah. No, but first, only when the lecturer goes too slow. You should look through this. Okay. So now a subset sum problem, but I wrote this problem in the back, I think. Yeah, that's why I thought about it. Yeah, the last one. And so you're given some number T. Oh, so let me write it for the people at home. So input. Input are a bunch of integers, the question and a target value. And the question is, can you get a subset, actually a sublist of these integers whose sum equals to the target? Input, so there is a 0, a 1, and so on. Oh, it's called it T, a n in natural numbers. And then the question, does there exist I, a subset of 1 to n, such that sum ai for I in the subset is equal to. Okay, I know that these numbers here are given in binary, right? If they're given in unary, what do you know about this problem? Can it be NP-hard, this problem in unary?
then it's polynomial time problem because.
Yeah, solvable. Like in the algorithmic course, it's always the same example for dynamic programming. Like or knapsack, maybe you have solved by dynamic programming. A special case, if value and weight is equal to t, then this is knapsack problem. If all values and weights are equal.
I would target that like it would have those numbers in unary, then the well, we know that it's like normal version is NP hard, NP problem, then it's but then we have like we replace an input with exponential of input, and so since NP lies in X. No. Doesn't P lies in class E.
Yeah. NP is subset of E.
Yeah, okay, then it's just directification.
Yeah. Okay, so we have to build reduction now from this problem to this problem. Okay, how will we create the numbers? We will write all the clauses in a table like this. Imagine we have k clauses like this. And then we will create, for each variable, we will create two numbers. And the numbers in decimal notation will be equal to indicator whether the literal is in the clause. So given our example, I delete the example. And so imagine the first variable is x, and x appears positive in 1 and negative in 2, and maybe positive in the last one. Then decimal expansion of our number will be 1, 0. Let's have more clauses. Like this. So x will be just this number. So then for not x, we will also make a number. It will be equal to all clauses that contain not x. Something like this. And we do this for all literals. Like this. And then the target value will be, sorry, we don't have negated literals. So we don't need this, just for every variable. Let's have ay. And because we have positive 1 and 3 set, there are no negations. And then the target value will be, what do you think will be the target value?
All ones.
All ones, yes, indeed. And that's the reduction, that's it.
Well, exactly. Those are binary numbers, not decimal.
Yeah, decimal numbers and base 10 here. We use.
Why
It's
base?
binary doesn't work.
Why?
Okay, that's a good question. So why is this reduction correct?
No, why it's just correct? It's clear for decimal numbers, but it's not clear why binary numbers doesn't work.
Okay. Yeah, but let's go over both directions. Okay, if we have positive 1 and 3 set assignment, then what will be our subset I? It will correspond to all variables set to true. So if x is set to true, then we have, for example, this one. If z is set to true, this one. And so we know in every clause there is precisely one true literal. So when we make the sum, we use primary school algorithm, and we get all ones, and we are good. Right? In every clause, there is precisely one true literal. So in every scale of magnitude, and here we have unity, tens, hundreds, thousand, and so on, there will be precisely one. However, and so now the other direction. Imagine subset sum exists, then we have a satisfying assignment. And now the idea is to follow, again, primary school algorithm, but we must ensure there are no carry bits. Otherwise, the proof is screwed. And so we check the least significant bit, and we say that, okay, since the unities must end to 1, we must have exactly 1, 1. But if we use binary addition, then we have a problem, because if we have 3 ones, then it is not exactly 1 and 3 set assignment. So, okay.
So the base should be at least 3. No, at least 4.
Yeah, base 3 works.
Base 3 can work well.
Base 3, then we have 3 ones.
3 ones and different close.
to zero, yeah, but that's
Ah,
not
yeah, that's the
considered, yeah,
Okay.
okay. Oh, that goes very well.
No, wait, it can be something like, it's very close to zero, but there is, but another one comes, from the previous.
No, no, but we need to start, let's start in our proof, we start with least significant bit.
Yeah,
So here, if it overflows, we have a zero
okay, yeah,
and we lose.
yeah.
So first cannot overflow
It's
and
cannot
by
overflow.
induction, yeah. Okay, but this is not important. I mean, just base 10 is enough. Okay. And then in the seminar, there is reduction from subset sum to knapsack. Okay, very good. And now let's, there is one problem left, this Hamiltonian cycle problem. So which is closely related to traveling salesman problem. So it also in the seminar proved that the traveling salesman problem is NP complete. And so it is reduction from Hamiltonian cycle. How does it work? Where is eraser?
Okay.
Sorry, thank you. Okay. And so we will do direction directly from Teresa. And so now there is 5-minute break because I will just draw the reduction on example and it takes a long time. And but then when I make the picture, it's clear. So that okay, so can wake up. Yeah.
Reconnect those.
Also, yeah, it's I missed some connection. So X appears positively and then we let's use another color. And X is in the second one negative. And then we go here. And go here. And the first one says Y positive. We have to go then it's y negative. Okay, new attempt.
I wondered how this construction would come into someone's mind.
No, it's normal. If you do this for a long time, your mind knows how to build pieces of graphs and so on. It's no problem. There are many cases where I really see paper, I really think that this guy must, how did he invent this? But here it's okay. So there are two gadgets. So it's normal when you do reduction on a graph problem, you create little graphs corresponding to variables and clauses. And so the variable gadget, it's kind of like a chain like this. So arrows on the top in one direction and then arrows that return.
Chain of what size?
Yes, so just long enough a chain for the connections with the clause gadgets. And the rule is that whenever you do something like between starting and so on, you leave a note in between. So here I need to connect to, so there are two clauses say that contain X. So I make a connection gadget between this clause. And I need the second connection gadget for not X here. And I just leave one such note in the middle. And also at the end, I leave one such note. Okay. So clause gadgets are clear. That's just a note. I already, the connection is also clear. So when X appears positively, we will replace like a top edge, give an alternative path for the top edge that visits the clause node. And when it's negatively, we replace an edge that goes in the other direction. And the plan is to force, so when we create the cycle, to either go in this direction or in this direction.
Corresponds to if
Yeah.
the literal is true or false.
Yeah. So in the variable gadgets, we can only go down. And we can only move vertically when we visit clause gadgets. But I will now explain that whenever one edge of a black pair is used, the other also needs to be used. So why is this? And this is by a very simple
So
observation.
it's actually a reduction from three,
Yeah.
like one three step actually.
So imagine that we have a graph of this form. So there are many nodes here and so on. Like this. So we have complex graph here and we see a node, we see a dangling node on two edges. We immediately know this graph has no Hamiltonian cycle, right? And this is the idea of our construction. And we must avoid such forms while constructing a cycle. And so I claim that when we visit this node, we are forced, so it only has two outgoing edges. So either we go left or right, so this is clear. But when we go here, I claim that we are forced to go to the right after we arrive here. And why is it? So imagine we don't go to the right and we go down. What happens is these edges can never again be used, right? If we go down, but then we have such dangling loop. Well, not really loop, but okay, you get it. Right? Such dangling thing. So when we arrive here, we must go right. And so now our moves, further moves will also be forced. So when we go right, we can no longer return. When we arrive here, we have a choice. We might visit this node, yes or no. If we decide to visit this node, then the claim is that we must return by the other black edge. Why? So imagine that we go from here to the black node, we follow this node. So at this moment, the black edge no longer exists. And imagine that I promise not to use this other black edge. So then I will temporarily remove it. these two blue edges can also not be used because I went there. So later in the cycle, I need to return here, but now we have dangling node again. Right?
Why can't we use that another arrow that goes from the close to the
And so what I'm saying is let's start here and start to this construct the cycle.
Oh, yeah, I get it. But if we go in the
If we go on the
class,
yeah.
and then we like return
Yeah, imagine that we decide
not
to return somewhere. Okay.
not to return immediately.
Okay.
Maybe we could return later.
Yeah. Imagine that we never. Yeah, we could maybe return somewhere else.
Okay.
No, well, sorry, you have to be careful. So the first step of the argument is, imagine we will never use this
Never.
edge.
Okay. If we never use
Never
it's
use,
clear.
yeah.
We can use it later. Like we
Okay,
go
but
there, then
when we arrive here, that's our only chance to use it. Because when we arrive
because
here,
we want because
yeah,
we want
the
to-
start
oh,
node of the edge will be
yeah.
used already. Yeah, so we must immediately return. And so when we decide, okay. And so if you understand this, you understand everything.
Well, it's actually not, the restart is actually one restart because it will be exactly one, but we will choose exactly what time now.
Oh, we can.
Oh, okay, no.
Yeah, I could do the reduction from one positive 1 and 3 set as well. It would also. And oh yeah, then the other direction is the problem. Yeah. Okay, so let's finish the argument. So of course,
Yeah.
this is polynomial time reduction. We build it in polynomial time. Then if we have assignment, then we understand how to visit all the closed gadgets exactly once while going through the variable gadgets, right? And so you just cycle according to the assignments. You go right when it's positive, left when it's negative. And so each time you choose the direction. If x is negative, we go like this and go like this. If y is positive, we go like this. So each time we can either oh, I forgot some edges here, sorry. So we have two choices. Oh, that's not cool.
On which vertices this is attached
To the top.
to the black edge.
The black edges. So yeah, that's the idea. For every clause, we will make for every variable in a clause, we make a connection gadget, just a pair of edges. And we go from the clause to the variable gadget. So for example, X appears in this clause, so we must connect it to this gadget. Not X appears here, we connect it, but replacing another in this direction.
This like the number of balls.
Yeah. So number of black arrows, black pairs is equal to number of literals in the formula. So clearly polynomial. So then the total length of all the
It's really clear.
Yeah. Okay, I forgot which direction. So if we have assignment, we can create a cycle.
Yeah.
If we have a cycle,
Yeah.
then the explanation says that then it's again by this explanation, and that we know that that we are forced to go either like this all the way or like this all the way, and from this we get this sign. Okay, that's it. So that was the plan for the lecture. We are 20 minutes early, but it is good because then I can speak a bit about circuit complexity. That's the topic of next lecture, but there is nothing from it in the seminar. I mean, the seminar exercises will be next time. So, why a circuit is really important to model. So there are people in St. Petersburg, they want to solve P versus NP problem. And so they are trying to find a problem that doesn't have polynomial sized circuits. And we will see if a problem has polynomial size circuits, then it's solvable in polynomial time. And we can evaluate circuits if we can. And so if it's in polynomial time, then we can build a circuit that simulates it. So why do we use circuits? To have a clean proof that 3 set is NP complete. And why a third reason why circuits are important, very important, is if you want to prove that a certain problem cannot be solved in parallelized way. So circuits is so in your computer, the addition multiplication is so often needed that on your CPU, people are ready to reserve big place to do addition and multiplication fast. And so they want to build a circuit of very small depth because that provide fast answers. So if you need to wait for an addition, if the addition is blocking further computation, it's important to send it to your special circuit and get the answer fast. Okay, nowadays there are all these special classes for parallel computation. It's kind of annoying to memorize them. But if it's done with circuits, I'm always happy to read the paper because it's very simple definition. Okay, so let's say what is formal definition of circuit. It's directed graph, but you already learned this. It's directed acyclic graph, so there are no directed cycles. There are 2 types of nodes called input nodes. They have fan-in 0, the input nodes. They don't have incoming edges. And then the other nodes are called gates, and they can have arbitrary fan-in. So there is NOT gates that have fan-in 1, of course, AND gate and OR gate, they have fan-in at least 2, but it can in principle be unbounded. There will be 2 types of circuit, bounded and unbounded fan-in. Okay, so let us write down a circuit that evaluates XOR, addition modulo 2 of 2 bits using an and OR gate. But maybe this was in discrete math course. So there are 2 bits, X and Y, and then the circuit will be altered. So usually circuits are drawn from bottom to top. Here are the bits, and then we will have an AND gate. That's right. So, so to implement XOR, we need also a negation. Something like this, right? And also some negation like this, and then an OR here. So this will do modulo 2. If inputs are equal, we have 0. If they're different, we have 1. At least I hope so. So if they're different, then one of them will be 1. Yeah. Okay. So we can build a circuit for addition. But wait, first. So what is size of circuit? Number of gates. So we don't count the input nodes. The depth of circuit is the length of longest path. So note that if I don't draw any edges, so computation goes upward. Edges are upwards or downward. I don't know what is the. It's always in layers, the circuit. Okay, and when we so usually that there is a general convention that for counting the size, we don't count the negation gates because we can always push them near the inputs. So number of negation gates, we can bound them by the number of inputs, and usually there's a small.
Why can't we do that?
So it's the Morgan rule. So we have A and B, and so if this is
Wait,
negated.
but if, but it could increase the number
A
of.
or B,
the number
so we
of-
push them all down so that they happen right at the inputs. So for every input, we create a second node that's the negation of the input.
Why won't it increase the number of gates? Because like,
So it can increase the number of gates, but only a little bit, only by the number of inputs. And this is increase, that's technically not interesting. So yes, this modern convention, you are allowed to ignore negations for depth and size.
that you get. Why does?
So it will never happen that the size goes from n to n squared
But and squared why?
by
I
pushing down.
get why it doesn't increase much than twice.
Yeah, so if you apply Morgan rule, negation gates can temporarily increase a lot. But when you push them down in the circuit, eventually they will arrive next to input nodes.
So
It's
not-
circuit, not
from-
formula. It's not a circuit, so you can reuse the outputs.
Yeah. Like if we reuse it the card. It's not really a problem.
Yeah, so by ignoring negations, the minimal size of circuit increases by at most number of inputs. Okay, let's continue. Okay, we can build a circuit for addition of numbers in binary. So we are given next. So for this one, like okay, once we have built a little, here we have a XOR gate. We can also get the XOR gate modulo 3, which is convenient for addition. So we have X, Y, and Z. So let's replace this by XOR of X, Y. And then we use two XOR gates. Okay. If it's boring, you can do the seminar. So then we have XOR of 3 gates. We can also, for addition, we also need a little bit, so to check whether the outcome is at least 2. So we also need the threshold gate. Threshold gate is checking whether at least a certain number of the inputs is set to 1. So if the sum of the inputs is at least a certain threshold. So we need a threshold gate on 3 nodes to check whether at least 2 of them are equal to 2. So let us call this gate T2, and then we can build the circuit for addition. So the input will be X1, Y1. Oh, let's start from the other side. X1, Y1. X2, Y2. Okay, so just a primary school algorithm can be implemented. I don't need to draw it, right? You have enough imagination. So each time you create the carry bit and the parity. And in this way, you can build a circuit that has many output nodes and computes the sum of the 2 nodes. So what will be if you have a circuit for inputs of length n? So what will be the depth? Will it be linear, quadratic? Linear.
It can be, but it can be done in logarithm.
Yeah, and the size will be linear, quadratic,
Size will be linear,
also linear. Okay.
but it can be done in logarithmic that. Like by splitting a number into 2.
Yeah. So people agree? What you say, you can use logarithmic depth. And if you have unbounded fan-in, so if you allow for big ORs, you can do it in constant depth. And even with linear number of gates. But this is like more advanced. So in the seminar next week, there is constant depth circuit. But then total number of gates linear,
Adding.
yeah, is not in the seminar. Because I mean, I could do it, but it's like borderline. It's maybe extra question or something, but I'm sure it's everywhere on the internet because it's such a common circuit.
If we could have the gates with arbitrary number of inputs.
Yeah, so we have or, yeah, with arbitrarily
Only
number and
or.
or and with arbitrarily fin.
Then it can turn.
Yeah. Okay, so
Awesome,
now
that.
it's time to say what are classes NCI and ACI. So NCI, well, first, let us say that, sorry, what do I want to say? Okay, all right. Yeah, okay. So when we have a problem, so we want to say is Hamiltonian cycle problem, does it have circuits of logarithmic depth? So probably not, but so for this, we don't need one circuit, we need a whole family of circuits. For each input length, we need a circuit. So, okay, let us first define the class P/poly. So we say that a language L is in P/poly if we have a family of circuits that solve the problem L on, so the N circuit solves a problem, decision problem for L on inputs of length N for N bit strings. And so if we have a family and the size of this circuit grows polynomially, then we say L is in P/poly. And note that we only require the circuit to exist. So we don't need to produce the circuit. And this means that there are undecidable problems in P/poly. But still, it's a useful class. So we say that L is in P/poly if there exists circuit 1, circuit 2, and so on, such that for all N, and for all X of length N, circuit N of X gives the correct answer. So L of X is indicator function for the language L of X. And so this is the first condition, and second condition.
We can, okay, get it. We can encode an infinite number of circuits into a machine. That's why it's
So this is short. There exists a polynomial such that for all N size of, as the N circuit is bounded by number of gates in the circuit is bounded by this. Okay. And so now there exists undecidable problem. So we can encode the halting problem in certain way so that it is in P/poly. So how would you do that? Kind of silly. And so actually you can code a halting problem in unary. So halting problem in unary is in P/poly. So what is this problem? So let us call it H tilde because we are messing with the unary notation. So we have 0p. So the program is interpreted in a number in binary. And then we use this length. So just a universal Turing machine on input P halt. Okay, and this definition satisfies P/poly requirement. Okay, let me change it a little bit. Let's repeat the symbol 1. Then it's a little bit slightly easier. So actually we can, so for circuits of unbounded fan-in.
Well, okay, yeah, we can just have a circuit for each P. We have a circuit for these programs because like
yeah. So these are binary languages. If you use other alphabet, you first have to map to binary languages. So
well, but it's like
it's of course stupid, yeah. But there is also a class uniform P/poly And then you need a log space machine that prints the circuit.
It's not
This
even full, it's
definition.
actually all one because it doesn't depend.
Yeah, yeah, it's all one-sized circuit. And we just need to take the n of everything. So if P doesn't halt, then circuit P always says zero, a constant zero. Okay, we need to be a bit creative to create a constant zero, actually. So we just need to take one input and then connect with the n of its negation, and we have constant zero. Okay. But then otherwise, we have, if P halves, we just have to check whether we get all ones. And then we decide like, okay. Yes. So let us prove that there exist problems that are not in P/poly. So for every n, we can come up with a function that maps n-bit strings to 0 and 1, such that a smallest circuit is of size at least 2 to the power n divided by some polynomial.
We just count numbers.
Yeah. Yeah, that's the proof. So there is little lemma. Okay, I forgot to write it, but this is P/poly. This is our little lemma. And the side of it.
Wait, is halting problem decidable on circuits at all?
It is,
If we encode programs in binary, could we is the
no, then the halting problem is not in P/poly.
fully, but is it solvable on like is there any like if we remove the second condition?
Yeah, sorry, good question. Yeah, I should say it first. Okay, so every problem, so every function is computed by some circuit of exponential size.
Oh yeah, oh that's clear.
Yeah.
That's just because it's
Yeah, but it needs
because
to
there
be-
is a CNF for each function.
Yeah, that's the proof. Oh, you know already. And you too? So if I give you arbitrary function, do you know how to get a CNF formula that equals this? So I say I will say it, otherwise there will be a problem. Okay. So but by the way, there are careful notes about circuits. It's also there. But let us present the formula. So what we do, the formula is like this. So we have so we are given a formula that gets n bits inputs and maps to 0 or 1. And so the question is, how can we build a formula in CNF, Boolean formula, that is equal to this f? And this formula will be a big R. And all the R of big N's. And the plan is to brute force all possible inputs and check. So there will be an OR, and for every input that makes f evaluate to 1, we create a term that evaluates to 1. So let me write it not as Boolean formula, but like a mathematics notation. So we will take a big R over all strings y of length n. So our formula, let's say f of x, will be a union over all y in over the strings of length n. And we will check whether x is equal to y, all y, such that f of y is equal to 1. And here we will write a formula that checks x equals y. And so checking whether x equals y is check whether x1 equals y1 and xn equals yn. Okay, and what is Boolean formula that checks whether two variables are equal? And so there's a formula for this. We use some space. We use A or not B, and B or sorry, and not A or B. Oh, this is formula. It's true if and only if the bits A and B are equal. So all these little claims here, we can also write as Boolean formula. And what we obtain after we do the substitution, we obtain a big Boolean formula that's equal to f of x. So why it's equal to f of x? Well, if we give it f an input where it evaluates to 1, then the corresponding y equal to this x will produce a 1 here. And if formula is 0, then for all these clauses, this formula will evaluate to 0. So all these checks will evaluate to 0 and function will be 0. It's clear. Okay, but this is not an ICNF formula. I should do it better. So I think there is to get CNF formula, I should do kind of reverse, like check when the values are 0. And so I should take a union not when the values are 1, but when the values are 0, and take intersection here. And then I will have a big OR, I will have a big N. And when I apply this trick, there are just more N's here. Something is wrong. So I need to have an AND over all clauses that produce 0. And then yeah, okay.
It's just like do more than rule.
Yeah, I can also apply the, yeah.
We just invert the function and gets it's
No, but this is yeah, you can do it, but it will be a huge. Well, okay, yeah, right. So it's still exponential size. Yeah, that's also. I forgot what I wrote in the notes, so I'm sorry. Okay. Yeah, so please look in the notes, and then you have a nicer formula. But this proof also works, but it's not CNF. Oh, okay. So, and then next week I will explain you. So we know that there's always a formula of size 2 to the power n poly n. So by such a construction, actually 2 to the n times n. And then I will say that there are always functions of size, say, so for every n, we can present a function for which minimal circuit size is at least 2 to the power n divided by polynomial. So that's for next week. And then I will define the classes of problems with logarithmic depth. And then I will explain that P is a subset of P/poly. And after this proof is given, we are very close to proving that 3 set is NP complete. Okay, that's for next week.
You also said that. How do? What's the reduction from direct Hamiltonian cyclotron?
Yeah, I forgot to say, yeah, what's this reduction? Okay, so we have we have created a directed graph, and the idea is to turn directed graph and undirected graph, so by splitting every node into 3 nodes. So every node will become 3 nodes, and all the incoming edges are connected to the first node. And all outgoing edges are connected to the third node. And these nodes have just an edge like this. Okay, and why does it work? So when we arrive in a node from one of the incoming edges, and so there's the reduction. We make a reduction from directed Hamiltonian cycle to undirected Hamiltonian cycle, just by splitting the nodes into 3, connecting incoming edges to the first, outgoing edges to the second. Why does it work? Well, when we arrive in a node, we are forced to immediately visit this node. If we don't visit this node, what happens? It means that we will never use this edge again. And now we have a graph with a dangling edge, which cannot, with a dangling node, I mean. And so we have a graph with a dangling node here. And there is no chance anymore to visit this node. as part of a Hamiltonian path. So that's the idea. But okay, I will just ask about directed Hamiltonian cycle because this is kind of annoying details here. Okay, I am this, so we are 5 minutes late now, so let's start the seminar at 7:45. And I will start the seminar because there was some exam that so if Yaroslav is now tortured by about his progress. So okay, so see you in 10 minutes.